In this video I'm going to explain how the helicopter code works. The helicopter we've seen here is controlled by the mouse. If the mouse is in the if the mouse is at the bottom of the window, bottom of the canvas, the engine is off, and if the mouse is at the top, it takes off. The engines are at full. So that's your throttle control, up and down. The tilting is left and right. So throttle is up and down, and the tilting is left and right. When it hits the ground, the collision speed is displayed there. Now we'll look at how the code works. So we've got this. At the top, you've got document type, you've got HTML. All these are tags, and for every start tag there's a closing tag. So there's the closing HTML, and then there's a head and a closing head, and then a body, and then a closing body. All your web pages are in the same format. This is quite standard. So now I'm going to delete the bits that you don't need to know anything about, which is basically all this stuff here. Everything above that line, everything above this line you can ignore. Everything below this line can be ignored. Literally, you've just got a canvas down there, and the width of the canvas is 800 pixels, and the height of the canvas is 600 pixels. But it can all be, you're not going to change that. You're only going to change the bit in between, which are the variables that you're using, and Newton's laws down here. This flowchart shows what's happening. At the beginning, the variables are declared and the values are set over here. Then the start function is run once. So any initial conditions you want can go in there. After that, the loop is run, which is everything from this bracket to that bracket. And then it waits for 50 milliseconds. The 50 milliseconds is defined up here. That's 0.05 seconds, and then it goes back round to the beginning of the loop, and it keeps going round there ad infinitum, until the program is stopped. So it will keep doing the loop over and over again. This bit loads in the pictures, the scenery, which is a JPEG, and the helicopter, which is a PNG. And down below, inside the loop, they are drawn. The scenery is drawn here, and the helicopter is drawn there. The scenery is put on first, and then the helicopter is drawn on top of it because it comes afterwards in the code. These bits highlighted are the labels. You've got a couple of labels drawn onto the screen here, and you've got a couple of text boxes there. So they come from this bit here. That's the landing, that's when it hits the ground, that's the label for that. The collision speed is displayed. But you won't need that, so we'll get rid of it. But what we are left with is two lines down here, which draws the those two labels, the thrust and the Y position on the screen here and here. And that's where they come from. Draw text. T to fixed means 0 decimal points, and to fix 3 means three digits after the decimal point, and that's the position, the X and the Y position for where the label is going to appear. These are some of the constants we're using. dt is the time interval, m is the mass, t is the throttle, goes between 0 and 100. It's the mouse Y position, which is being divided by 3. So 100 take away the Y position, divided by 3 gives the throttle. R is the rotation of the helicopter. in degrees. So if the mouse is at 400, then that would be 0. If the throttle was at 100, that would be the throttle would be 0. I don't know if that makes any sense, but the top left-hand corner of the screen is where the 0, 0 point is. So here, top left-hand corner of the screen is 0, 0. X is the horizontal distance from the top left-hand corner. By the screen I'm referring to this picture here. That's the 0, 0, top left-hand corner. Y is the vertical distance from the top of the screen downwards. Vx is the horizontal velocity, Vy is the vertical velocity, Ax and Ay are the accelerations used down here in Newton's laws. So here we get the two user inputs for throttle and the tilt to the helicopter. Here we set the limits. We say if the throttle is greater than 100, we limit it to 100. If it's less than 0, we limit it to 0. If the rotation is greater than 0, we limit it to a function of the height. But again, you don't need to know much about that. The lift is equal to some constant times the throttle. So 100% throttle, we would have 100 times 20 times 200, and that would be the lift in newtons. Down here we then implement Newton's laws. This bit at the bottom is the friction. When the altitude is on the ground, the acceleration is 0 and the velocity reduces. But these 6 lines here are the crucial ones. The top line is nothing more than F equals ma, rearranged to give acceleration, which is equal to the force divided by the mass. The force is equal to the lift component of the lift in the vertical direction, taking into account the tilt of the aircraft, the tilt of the helicopter, and then divided by the mass. By tilt I mean if the helicopter is at an angle of theta and there's lift, then the component of theta in the vertical direction is L sine theta, and the component in the horizontal direction, this direction, is L the vertical one is L cos theta and the horizontal one is L sine theta. So Ax depends on L sine theta and the lift depends on L cos theta. So both of these are just F equals ma. The next couple of lines below describe the velocity. This is nothing more than v equals u plus at, and the one below that, the two below that are integrating. So each time around the loop we work out a new velocity depending upon the old velocity times acceleration times the time interval. We do that in both directions, in the x direction and in the y direction, and we do the same for the position. The position is the integration of the velocity with respect to time, which is what we're doing here, implemented in those 2 lines there. So that's just integration. The new position is equal to the old position plus the velocity over the time interval times the width of the time interval in seconds.